As with other things in deep learning, we can dig deeper into the learning rate schedules. Instead of using a simple rule to adjust the learning rate, we can use advanced academic research on this topic. We will consider two types of adaptive learning rates, AdaGrad and RMSprop. They build on each other, so it won't be too much to take in. Be prepared to see many formulas, although it's unnecessary to learn these by heart. In TensorFlow, you can simply say, use AdaGrad and the magic will happen. As usual, we recommend you go through the entire video, as what we will see is cutting-edge machine learning. When you practice machine learning, you must be able to choose the best methods for training your models. Alright, let's begin. First, we have the AdaGrad. AdaGrad is short for Adaptive Gradient Algorithm. It was proposed in 2011, so it is new. It dynamically varies the learning rate at each update and for every weight individually. So, the original rule was, stated otherwise, the change in W equals minus the learning rate times the partial derivative of the loss with respect to W. Nothing new so far. When we consider the adaptive gradient algorithm, the change in the weight will be given by the same expression, but in addition, it will be divided by the square root of g at time t plus epsilon. So what is g here? G is the adaptation magic. Gi at epoch t equals Gi at epoch t minus 1 plus the square of the gradient at epoch t. We begin at g not equal to 0. At each step, g increases because we are adding two non-negative numbers. Thus, g is a monotonously increasing function. Since we are dividing the learning rate, eta, by a monotonously increasing function, eta divided by that is obviously monotonously decreasing. If you are wondering, the epsilon is some small number we need to put there, because if g is 0, we won't be able to perform the division. Okay, that was AdaGrad. It is basically a smart adaptive learning rate scheduler. Adaptive stands for the fact that the effective learning rate is based on the training itself. It is not a preset learning schedule like the exponential one where all the eta values are calculated regardless of the training process. Another very important point is that the adaptation is per weight. This means every individual weight in the whole network keeps track of its own g function to normalize its own steps. It's an important observation, as different weights do not reach their optimal value simultaneously. The second method is RMSprop, or the root mean square propagation. It is very similar to AdaGrad. The update rule is defined in the same way, but the g function is a bit different. The two terms are assigned weights, beta and 1 minus beta respectively, effectively keeping track of a moving average of the g values. This new hyperparameter beta is a number between 0 and 1. The value 0.9 is very typical. We had a similar situation with the alpha in the momentum section. The great implication here is that the function is no longer monotonously increasing. Hence, eta divided by the square root of g is not monotonously decreasing. Empirical evidence shows that, in this way, the rate adapts much more efficiently. Okay, both methods are very logical and smart. However, there is a third method based on these two, which is superior. We will explore it in our next lecture. Thanks for watching.